the lights do not flicker first. That is the myth. In a true grid failure, especially a cascading collapse, illumination does not politely dim to warn you. It vanishes. 1 second the refrigerator compressor hums, the router blinks green, the streetlights glow sodium orange against the asphalt, and the next second the entire electrical ecosystem goes silent. The silence is what people remember later. The hum disappears. The background vibration of civilization stops. In that vacuum, elevators freeze between floors, fuel pumps lock mid-transaction, hospital monitors switch to battery without ceremony, and the illusion of permanence fractures. Day zero is not the moment society collapses. It is the moment the grid stops responding. To understand what happens next, you have to understand how the grid actually works. Modern electrical grids are synchronized machines operating at tightly regulated frequencies, 60 Hz in North America, 50 Hz in much of the rest of the world. Every generator connected to the network must spin in near-perfect harmony. If demand spikes unexpectedly or supply drops suddenly, frequency begins to drift. Protective relays are designed to detect that instability and disconnect components before they are physically damaged. This is not a flaw, it is a safety feature. But safety mechanisms cascade. When one transmission line trips offline, its load shifts to neighboring lines. If those lines exceed thermal limits, they trip as well. What looks like a single failure becomes a chain reaction governed by physics, not intent. Many people assume blackouts are caused primarily by sabotage or cyber attack. While digital threats are real and documented, most large-scale outages historically result from mundane forces, severe weather, vegetation contact, equipment aging, operator error, fuel supply constraints, or heat-driven demand surges. The hidden science is less dramatic but more instructive. Transmission lines expand when hot. Increased current increases resistance, which increases heat, which increases sag. A line sagging into a tree during peak demand can trigger a protective shutdown that cascades across states or provinces. Investigations into past grid collapses have repeatedly demonstrated this thermodynamic chain. The lesson is not paranoia, it is infrastructure fragility under load. Emergency planners do not assume the grid is immortal. They design around failure. Hospitals maintain redundant power through diesel generators sized to handle critical loads, not entire facilities. Data centers deploy uninterruptible power supplies. Battery arrays capable of carrying systems for minutes, sometimes hours, until backup generators reach operational speed. Water treatment plants, telecommunications hubs, financial clearinghouses, and air traffic control centers maintain layered contingencies. These plans are not secret in the conspiratorial sense. They are simply not discussed publicly in operational detail, because security requires discretion. But their existence is documented in engineering standards, federal emergency management frameworks, and reliability council requirements. The misunderstanding is that emergency power equals continuity. In reality, backup systems are designed for prioritization, not comfort. A hospital on generator power may shut down elective procedures and dim hallway lighting to conserve fuel. A cellular network under extended outage conditions may operate at reduced capacity as towers cycle power or rely on limited duration batteries. Fuel becomes the constraint variable. Diesel generators do not run indefinitely. They require resupply, and fuel distribution depends on the same electrical infrastructure that may be compromised. Pipelines use electrically driven pumps. Refineries rely on complex industrial power. Even fuel terminals require power to load tanker trucks. The grid underpins the fuel that powers the backup to the grid. Evidence from prolonged outages shows a predictable timeline. Within minutes, traffic signals fail unless backed by battery systems. Congestion spreads. Within hours, grocery stores begin closing as point of sale systems fail and refrigeration uncertainty rises. Within 24 hours, temperature-sensitive supply chains degrade. Within 48 hours in warm climates, food spoilage accelerates in households without generator support. Water systems with limited generator capacity may issue boil advisories if treatment stability wavers. Wastewater systems risk overflow if lift stations lose power. None of this requires societal breakdown, it requires time without electricity. The survival implication is not panic buying, it is energy literacy. Most households dramatically underestimate their daily kilowatt-hour consumption. A typical refrigerator may draw between 100 and 800 watts depending on compressor cycle. A well pump can demand several thousand watts on startup. Electric water heaters, HVAC compressors, and induction cooktops are high-load devices unsuited to small portable generators. The hidden principle here is starting current versus running current. Motors require a surge to overcome inertia. A generator rated for 3,000 watts continuous may trip when faced with a 6,000-watt startup spike. Without understanding load profiles, backup systems fail not because they are defective, but because expectations are misaligned with physics. Emergency power planning at the municipal level revolves around load shedding and black start capability. Black start refers to the ability of certain power plants to restart without external grid supply. Hydroelectric facilities often possess this capability because flowing water provides immediate mechanical energy. Some gas turbines can also be configured for black start using on-site diesel generators to initiate ignition and spin up. Coal and nuclear plants typically require external power to begin operations, which means they cannot simply restart themselves after a full grid collapse. Restoration follows a choreography: energize a small island of generation, stabilize frequency, gradually add load, synchronize additional plants, extend transmission corridors, and repeat. It is slow by necessity because imbalance risks another cascade. The escalation scenario that emergency managers quietly model is not a single region outage, but a multi-region disturbance compounded by extreme weather or fuel disruption. Heat waves increase air conditioning demand while reducing transmission efficiency. Cold snaps increase heating loads and strain natural gas supply as residential heating competes with power generation. Drought can limit hydroelectric output. These are documented operational constraints, not hypotheticals. When multiple stressors align, reserve margins shrink. Grid operators maintain contingency reserves precisely to absorb sudden loss of generation, but reserves are finite. The system is robust, yet not infinite. At the household level, the overlooked variable is time perception. In short outages, people conserve instinctively. In longer ones, behavior shifts. Battery banks drain from constant phone charging. Vehicle fuel is wasted idling for air conditioning. Portable generators run continuously instead of intermittently, consuming fuel at unsustainable rates. The hidden science here involves duty cycles. Refrigerators do not need constant power, they need periodic cooling. Rotating loads strategically can extend limited fuel supplies significantly. This principle is used in disaster field hospitals and remote scientific stations: power in pulses, preserve thermal mass, minimize continuous draw. Evidence from emergency response doctrine emphasizes redundancy in layers: grid power, on-site generation, mobile generators, mutual aid compacts between states or regions, prioritized fuel contracts, and critical infrastructure designation. These layers are codified in national reliability standards and disaster response frameworks. What the public rarely sees is the tabletop exercises where cascading scenarios are modeled repeatedly. Utilities simulate transformer failures, cyber intrusions, geomagnetic disturbances, and coordinated physical attacks not because they expect apocalypse daily, but because complex systems require rehearsal. The survival implication escalates when we consider transformer vulnerability. High-voltage transformers are massive, custom-built machines that can weigh hundreds of tons. Manufacturing lead times can stretch many months. They are protected by physical security measures and monitoring, yet they remain single points of failure in certain corridors. A severe geomagnetic storm induced by solar activity can generate currents in long transmission lines, saturating transformer cores and causing overheating. This phenomenon is documented in space weather research and past events, including regional blackouts triggered by geomagnetic disturbance. Utilities mitigate this risk with monitoring systems and operational procedures to temporarily reduce load during solar storm alerts. But the physics cannot be negotiated, it must be managed. As we move deeper into electrification, electric vehicles, heat pumps, data centers powering artificial intelligence models, the baseline demand curve shifts upward. Grid modernization efforts aim to integrate distributed energy resources like rooftop solar and battery storage, which can provide localized resilience. However, distributed systems introduce new coordination challenges. Inverters must synchronize frequency. Protection schemes must detect islanding conditions to prevent backfeeding lines under repair. The misunderstanding is that more solar panels automatically equal independence. In reality, most grid-tied solar systems shut down during outages unless paired with storage and isolation equipment, precisely to protect line workers. The hidden science of microgrids offers a glimpse of controlled autonomy. A microgrid can disconnect from the main grid and operate independently if generation and load are balanced internally. Universities, military bases, and some hospitals have implemented microgrid architectures to enhance resilience. Evidence from pilot programs demonstrates reduced outage impact when properly engineered. But microgrids are not spontaneous. They require careful planning, investment, and regulatory approval. They function because of engineering discipline, not improvisation. The escalation continues when communication networks degrade. Fiber optic cables carry data as light pulses, but the switches and amplifiers along the route require power. Satellite ground stations require power. Even cloud infrastructure is anchored in data centers dependent on layered electrical redundancy. In prolonged outages, digital isolation compounds physical isolation. Information scarcity accelerates rumor formation. The survival implication becomes psychological as much as logistical. Clear, verified information reduces panic behavior that strains limited resources. Day zero blackout is not a cinematic explosion. It is a systems failure governed by load curves, thermal limits, fuel logistics, synchronization tolerances, and human response patterns. The emergency power plans exist not as secret escape routes for elites, but as structured prioritization matrices to preserve life, sustaining services first. Critical care, water purification, emergency response coordination. These receive power before shopping centers or decorative lighting. This prioritization can feel abrupt to those unaccustomed to scarcity, yet it is rooted in ethical triage principles established in disaster medicine and civil engineering. The transition from stability to vulnerability is subtle, because modern life hides its dependencies behind walls and firmware. You do not see the substations stepping voltage down from hundreds of kilovolts to neighborhood levels. You do not hear the automatic generation control signals adjusting turbine output in milliseconds. You do not notice frequency drifting by fractions of a hertz as operators intervene. But when intervention fails or delay accumulates, the silence returns. And in that silence, preparedness shifts from abstract concept to immediate calculation. How much stored energy exists within reach? How efficiently can it be used? How long can critical needs be sustained before restoration sequences reassemble the machine? The next layer of analysis is not whether the blackout can happen. It has happened, repeatedly, in different forms and durations across continents. The real question is how emergency power hierarchies interact with public expectation under stress, and what that means when restoration is measured not in hours, but in days. Restoration measured in days changes human behavior more than restoration measured in hours. When people believe power will return quickly, they conserve instinctively and wait. When the timeline becomes uncertain, consumption patterns distort. This is not speculation. It is documented in post-disaster behavioral studies conducted after hurricanes, ice storms, and regional grid collapses. The danger phase emerges not from darkness itself, but from cascading dependency failure. Refrigeration falters, electronic payment systems stall, supply deliveries pause, and medical devices in private homes begin counting down battery reserves. Oxygen concentrators, dialysis support equipment, powered wheelchairs, insulin refrigeration. These are not abstract conveniences but life-sustaining technologies integrated into domestic environments. Emergency power planning at the national level accounts for hospitals, but decentralized medical dependence introduces complexity that centralized planning cannot fully see. The analytical reality is that electrical grids are designed around probabilistic reliability standards. In North America, Organizations like the North American Electric Reliability Corporation establish criteria requiring utilities to withstand the loss of a single major component without cascading failure, a principle often referred to as N1 contingency planning. Some critical corridors are engineered for N2 scenarios, meaning they can tolerate two simultaneous failures. However, statistical design does not eliminate risk, it reduces it to acceptable thresholds based on cost-benefit modeling. Absolute redundancy is economically and physically impossible. Transmission infrastructure spans vast geographic areas, exposed to weather extremes and geological variability. Every additional layer of redundancy adds cost, maintenance burden, and complexity, which itself introduces new failure modes. A widespread misunderstanding is that the grid operates as a single monolithic machine. In practice, it is segmented into interconnections, large synchronized regions linked by high-voltage transmission corridors. In North America, the Eastern Interconnection, the Western Interconnection, and the ERCOT grid in Texas operate largely independently. If one interconnection collapses, others are not automatically pulled down, though limited ties exist. This segmentation is a resilience feature born of engineering pragmatism. The hidden science lies in synchronization physics. Alternating current systems must match phase and frequency precisely to interconnect. If frequency diverges beyond tolerance, protective systems isolate regions to prevent mechanical destruction of turbines and generators. Evidence from past cold weather grid crises demonstrates how fuel supply intertwines with electricity in a circular dependency. Natural gas-fired plants depend on pipeline pressure maintained by electrically powered compressors. During extreme cold events, residential heating demand increases gas consumption, reducing pipeline pressure available for power generation. If electrical outages reduce compressor operation, pipeline capacity shrinks further. This feedback loop is a documented systems interaction. Emergency management frameworks respond by prioritizing critical compressor stations and key substations for backup power support. Yet prioritization is triage. Not every node can be hardened equally. The survival implication is that resilience is layered geographically and socially. Urban centers with dense infrastructure often receive restoration priority due to population density and critical services concentration. Rural areas, served by long radial distribution lines, may experience longer restoration times because each mile of line must be inspected and repaired manually. This is not neglect, it is logistical sequencing. Line crews must ensure safety before re-energizing circuits. Downed lines can backfeed from private generators if transfer switches are improperly installed, creating lethal hazards. The hidden principle here is isolation integrity. Properly engineered transfer switches physically disconnect a home from the grid before generator power engages, preventing unintended energization of utility lines. Misunderstanding persists around portable generators operating inside enclosed spaces. Carbon monoxide poisoning spikes dramatically during extended outages, as documented by public health agencies following major storms. The chemistry is straightforward. Incomplete combustion produces carbon monoxide, an odorless gas that binds hemoglobin more effectively than oxygen, leading to hypoxia without warning. The scientific explanation is well established, yet behavioral lapses occur under stress. Emergency messaging repeatedly emphasizes outdoor placement and proper ventilation because even partially enclosed garages accumulate lethal concentrations quickly. Escalation intensifies when we examine water systems. Municipal water relies on electrically driven pumps to maintain pressure and move water through treatment processes. Elevated storage tanks provide gravity-fed buffer capacity, but without pump replenishment, reserves deplete. Wastewater systems depend on lift stations to move sewage across elevation changes. Extended outages risk sanitary system failures that create public health hazards independent of the initial electrical cause. Evidence from hurricane-impacted regions shows that boil water advisories often follow prolonged power disruptions due to treatment plant instability. This is not a collapse of civilization. It is a predictable consequence of pump interruption. The hidden science of thermal inertia becomes critical inside homes. Refrigerators and freezers maintain safe temperatures not through constant cooling, but through insulation and stored cold mass. Each door opening exchanges dense cold air for warmer ambient air, accelerating temperature rise. Food safety guidelines are based on bacterial growth curves that increase exponentially in the temperature danger zone between roughly 4 degrees C and 60 degrees C. Understanding these microbiological thresholds allows households to make rational decisions about food preservation rather than discarding supplies prematurely or consuming unsafe items. The danger is not darkness, it is invisible bacterial replication driven by thermodynamics. As outage duration extends, fuel logistics surface again. Gas stations rely on electric pumps to dispense fuel. Some jurisdictions mandate backup generators at key fueling stations to support emergency vehicles, but private vehicle access may remain limited. This creates a mobility constraint that alters evacuation calculus. Emergency planners evaluate contraflow traffic management for hurricane evacuations, but unplanned blackouts introduce decentralized decision-making. Evidence indicates that early, orderly movement reduces congestion, while delayed mass departure increases gridlock risk. The survival implication becomes anticipatory action rather than reactive escape. Communication degradation adds another layer. Cellular towers typically possess battery backup ranging from a few hours to perhaps a day, depending on configuration and load. Some critical towers integrate generators, but refueling remains necessary. As batteries deplete, towers may reduce broadcast power or shut down entirely. Text messaging often succeeds when voice calls fail because it requires less bandwidth and can queue data packets. This behavior is rooted in network architecture and load balancing algorithms. The hidden principle is that communication systems prioritize efficiency under constraint, but they cannot operate without physical power. Escalation at the institutional level involves black start sequencing under constrained conditions. Hydroelectric facilities, where available, often serve as anchors because flowing water provides immediate torque without combustion delay. Once a stable island is formed, operators gradually add load, carefully monitoring frequency response. If load exceeds generation capacity too quickly, frequency drops, risking protective shutdown. This balancing act requires precise coordination across control rooms, guided by supervisory control and data acquisition systems. Those systems themselves depend on backup power and redundant communication pathways. Evidence from grid restoration manuals emphasizes slow, deliberate re-energization to avoid secondary cascades. A frequent misconception is that renewable energy inherently destabilizes restoration. In reality, inverter-based resources can contribute to grid stability when properly configured with grid-forming capabilities. Advances in power electronics allow certain battery systems to provide synthetic inertia, mimicking the stabilizing effect of rotating mass in traditional turbines. The hidden science involves rapid response algorithms that inject or absorb power within milliseconds to counter frequency deviations. Pilot deployments demonstrate promising resilience potential, though integration requires updated protection schemes and regulatory adaptation. Survival implications expand into temperature control. In heat waves, loss of air conditioning increases heat-related illness risk, particularly among elderly populations. Human thermoregulation depends on evaporation and convection. High humidity impairs evaporative cooling efficiency. Urban heat island effects amplify ambient temperatures in dense cities. Emergency response plans often designate cooling centers powered by generators to mitigate mortality risk. Conversely, in cold climates, electric heating loss risks hypothermia and frozen plumbing. The physics of freezing water expanding inside pipes leads to rupture, causing flooding upon restoration. Insulating pipes and draining systems during extended cold outages becomes a rational mitigation step rooted in material science. The escalation scenario intensifies if blackout coincides with digital payment failure. Modern economies rely heavily on electronic transactions. Without power, point-of-sale terminals and ATMs cease operation. Cash becomes temporarily dominant, yet cash availability is limited by prior withdrawal patterns. This creates short-term liquidity friction. Emergency management guidelines encourage maintaining modest emergency cash reserves precisely for this contingency. The principle is not distrust of digital systems, but recognition of electrical dependence. Evidence from resilience research consistently shows that communities with strong social networks recover faster. Information sharing, resource pooling, and coordinated action reduce strain on emergency services. The hidden science intersects with sociology. Distributed resilience emerges from interpersonal trust and communication pathways. While infrastructure engineers focus on transformers and turbines, behavioral scientists emphasize cooperation under stress. Both domains converge during prolonged outages. The danger phase deepens if restoration timelines extend beyond fuel reserves for backup generators at critical facilities. Hospitals often maintain several days of diesel on site, sometimes more, depending on regulations and storage capacity. Refueling priority agreements exist between utilities, fuel distributors, and emergency management agencies. Yet large-scale transportation disruption can delay tanker delivery. Contingency plans may involve mobile generators transported from unaffected regions under mutual aid agreements. Evidence from disaster response demonstrates rapid interstate utility crew mobilization supported by pre-existing compacts. The hidden science of cascading infrastructure reveals a layered fragility. Electricity powers fuel systems, fuel powers generators, generators power water systems, water supports public health, and communication networks coordinate response. Each layer has redundancy, but redundancy is finite. The survival implication for individuals is proportional preparation, battery banks sized realistically for essential loads, safe generator operation practices, water storage calibrated to household consumption, thermal management strategies for climate extremes, and communication plans that assume intermittent connectivity. As the restoration choreography proceeds, operators gradually reintroduce neighborhoods to energized circuits. Sudden load pickup can stress transformers if too many devices restart simultaneously. Some utilities stagger restoration or advise residents to keep major appliances off during initial re-energization. The physics behind this guidance relates to inrush current and load diversity assumptions embedded in transformer design. When every compressor and heater engages at once after prolonged silence, peak demand temporarily exceeds normal diversity factors. The transition now moves toward a deeper examination of the emergency power plant itself, not as rumor, but as structured doctrine embedded in regulatory frameworks and engineering manuals. Understanding that plan requires examining how priority tiers are determined, how critical infrastructure is designated, and how restoration sequencing reflects life, safety hierarchy rather than economic hierarchy. In a prolonged day zero blackout, the question is not who has power first, but why certain circuits are energized before others, and what that reveals about the invisible architecture of survival engineered into the grid long before the lights went out.